Oh, let's see if everything's going on. Are we live? Okay, live. Bitrate seems good. Says our bitrate's high, but well, I guess things are gonna work out eventually. Not drop frames yet. Okay, so I'm gonna make this a pretty quick stream. I also make a habit of looking towards the camera and talking to the camera. I need to create better habits in this case if I'm going to start recording more. But yeah, I'm going to be talking about Rust, and I want to talk about it from a perspective that I don't think is represented well enough, which is a C programmer. How can I put this better in words? What I want to be able to do is be able to help C programmers understand a little bit how Rust works, and also how they can come into Rust using the knowledge that they already have. Because Rust and C and C++, I'm also talking to C++ people as well, but Rust, C, and C++ are all working in the same area. They're all low-level programming languages without a garbage collector and allow a lot of control at low-level functionality. So anywhere that you can use C or C++, you can use Rust as well. And of course, Rust doesn't have as mature of an ecosystem that C and C++ have, but that's just a matter of age. C++ is over 40 years old now. C reaching is over 50, reaching 60. So obviously, throughout, just as a matter of time, like you're going to have more resources available to you in those languages compared to Rust. But Rust is now 10 years old, and for programming languages, that's better than most because not many get to this level yet. And I know how you see programmers talk about us. I see what you say about Rust. And I feel like I have an interesting perspective to bring on this topic because I've been going back and forth between C and Rust. Like initially, when I learned programming, I learned in college writing C. That's what my professors taught me, and that's how I picked up most of the concepts and also some Java as well. And then I picked up PHP, JavaScript, Ruby, and got into web development and was able to, and that's where most of my career has been. But I've always enjoyed low level programming, and yeah, I've also had some, and that interest has actually benefited me throughout my career because it's like allowed me opportunities to like go really deep into like some lower level bindings, find some nasty errors that only come up when you're working at scale and like you're working at a company that is big enough for like these memory allocations to suddenly become a problem that you need to look into and make sure that you're doing things correctly or refactoring your code in a way that we can we're not like causing the virtual machine to pause and like crash it or not crash but like makes things works for the end users. And so I picked up Rust in like 2015 in my final year of college. I was always like keeping up with programming languages at the time what was coming out and just getting a handle on what's going on. And like Rust was the new kid on the block. Everybody was talking about it. It was all the buzz, all the rage, and I wanted to see what was going on. And I thought it was a very interesting concept at the time that I even used it in like my final project for school for graduation, where I was making a recommendation system and I wanted to like talk about service oriented architecture, and I made this a front end and back end in Ruby on Rails, showing like for you to like put in these data for the recommendation system, and then all the processing for that system. I could have done it in Ruby as well, but thankfully I didn't. And also that was the point I was trying to make with my essay, which was we can take advantage of like different programming languages to use them to like for the best situation that they're suited for. So in the case of Ruby, it would be for making these CRUD applications for creating, reading, updating, and deleting data. And Rust would be used for where we needed performance, which would be with this process, which would be doing all this linear algebra to make the calculations, to make recommendations at the time. And that was my initial experience with Rust. And it was a very fun experience, but like it was very much me like, when you're in the dark and you can't see anything, so you're just reaching out your arms and trying to figure out like how I can do something, like where am I going? Because I was already experienced with programming at the time. I was confident in myself to pick things up, and I knew how to like express the ideas that I wanted to actually put into action. But then like I went up against the bar checker and I lost a lot of times. There was a lot of dot clones everywhere to just get it done and get it functioning so I can present it to my teacher and be like, look at this cool thing that I came up with. And I haven't been able to work professionally in Rust yet, but it's always been something that I am just keeping up with, reading up on, doing a little pet projects on just to keep just practicing and trying to understand it as best as I can. Just like I also did with C, because I've been going back and forth between the two. Like I feel like both languages complement each other very well, and to learn one is to also learn the other, and they help. Like when you learn both, it kind of unlocks. It's like the yin and yang, where it's like you unlock a third thing, and it's just like you become enlightened. I don't know how to explain it, and uh, and so like I started with Rust, picked up Rust, was able to get a project working in it, but I knew myself that I didn't do it as well as I could have, and I got frustrated, and I was like, I better learn like C++ plus plus or C. There are more resources for that because Rust is a very young language at the time. And so I picked up those languages, I read up books on them, and I just also did the same thing, making small projects in them, writing a renderer. Uh, and with that, I became frustrated a lot with C. Mostly C because I didn't want to use C++ much because it was hard keeping up with like all the new updates and like modern C++ and like the rule of three, the rule of five, and like there's the rule of seven now, and just like it became a lot of it was a lot of cognitive overload to keep a lot of things in my head and be like, well, oh, and like you have to like remember all these edge cases for like situations that become and those become hard to remember when you're like writing code or until the bug becomes apparent and like causes a problem. So I primarily focus on C because I'm like, if I pick up C, if I ever eventually work with C++, it's kind of like rock Lee training with the weights on. It's like I'm intentionally doing something harder, and by doing so, like I understand and do it better when I'm not using those restrictions. And with uh, and playing around with C and using C, I also became frustrated as well. And that isn't to say that like C is a bad language, but C developers need to like be honest with themselves and just like admit that like there is a lot of things missing in their language, and I'm just like simply tired of re-implementing a lot of things from zero because that shouldn't be like my responsibility. I mean, like I, I can write my own array implementation, linked list, hash tables, index maps, all these different data structures. I know how to do these things, and I enjoy doing them. But there are also some things where it's like, look, I would like this to be something that's standard across the whole entire language by now, and that like everybody is building on top of these fundamental building blocks. And that's what brought me back to Rust, because I feel like Rust gives you like a lot of fundamental building blocks for low level programming that help bring in uh, foreign C code and C++ code as well, and like bring it into the Rust language in a very idiomatic way, or like make it so that like the code that is coming in from outside can be integrated into Rust so that it can be used idiomatically inside of the language. And that's what I'm going to be talking about. But the first thing that I want to talk about is actually something that I see a lot of C developers like not really understand, which is like safety and unsafety. Like what's like I feel like a lot of people assume that unsafe means bad and something that you don't do. And I want them to think of unsafety in like the same way that like you think of skydiving or like motocross or like an extreme sport. It's like it's unsafe, but that doesn't mean it's a bad thing. It's a pretty cool thing. It's like in the case of skydiving, I want to do that someday. And obviously like I have to be secure in that. I need to like take all the proper precautions. But just because it's unsafe doesn't mean it's bad. And maybe that's like maybe that's something that like the Rust community should do a better job of, and that's something like I'm putting out there to the rest of the Rust community, which is like, do we make unsafe seem like such a bad thing to do? Maybe we do sometimes because I feel like it's the common advice is like to never use unsafe, but like ultimately like all of the code is gonna like go down into something that is eventually unsafe. If you're doing a network code, it's eventually gonna make call like an internal system call, and that's gonna be unsafe code to run. It's like unsafe shouldn't be something that we avoid. It's something that we need to manage, and that's what I want to like make sure that other C programmers understand very well, which is unsafety is something that we manage and something that we avoid. So let me just start a project real quick over here, and let's start talking about how we can do things. So, cargo new, let's make a library crate. If you want to make an application or binary crate, you don't need this flag, but do that. Let's just call this. What's an interesting name? Let's call it Icarus. I don't know. This project's going to be called Icarus. And all projects will have these, it's going to already initialize Git for you. It's going to come with a cargo manifest for all the dependencies that you add to the project. And then a source folder where your code's going to be. And then over here, we have an example already generated to us by Ross, but let's just see all of it. And let me just look at some pull up a reference over here real quick. So I'm gonna actually be adding a crate level attribute to our library just for like educational purposes, because I want to actually go into the lower level code and explain some things from like the fundamentals instead of using what's in the standard library. So I'm going to put this no standard create attribute into our lib file, and that's just basically going to tell the compiler that we aren't linking to the standard library, we're linking to the core library. Now, the core library is in the standard library, but the standard library includes all of the cross-platform code or all the platform-specific code that you use in Rust. So like if you're going to make a thread, you're going to use the thread struct, and that's going to do all the work behind the scenes regardless of what operating system you're on to create a thread and for you to run the function that you pass it in that thread. And you don't have to worry about whether or not you're using like pthread create or what is in Windows, like create thread A or something. I forget what the Windows system call is. I don't use Windows that often, and I pretend to keep it that way. Like I think something a lot of people don't know is that like the core library is the is just like everything that is yeah. Hmm. I'm gonna have to come up with a better phrase or a better wording for it. But let's just say that like libcore are the fundamental building blocks of everything else that you see in Rust. And it's everything that isn't platform specific. So that's going to give us everything related to manipulating string or character sequences, so strings, uh, slices. Let me just pull up the reference real quick and make sure that I'm not like talking out my ass. So, and you can always go to the Rust documentation and pull this up as well to see for yourselves. But core exports very few modules, and it's just going to export like the traits that are universal across Rust, um, the any type, array type, cell, cloning, some markers, which are going to be something I talk about more in a later topic, and yeah, just the simple primitives that we have. Like we have the option type, result type, things related to asynchronous programming, which is not going to be in the scope of this talk, but it's everything that isn't platforms that doesn't get into platform code. So there's not going to be any networking code. There's not going to be any codes for creating threads. There's not going to be anything for calling or spawning a process. And also, none of the data structures that that Rust provides you in its standard library. So there's no hash map, there's no vector, because we are also not importing the alloc crate because the Rust standard library is like built on uh, it on Rust standard library is built on the core, which is like all these primitives, alloc, which is allocation and certain data structures that only need allocation and only need like uh, some different type of logic to work. Like in the case of a hash map, you would need a hash implementation, so it isn't in an alloc. But when you have a B-tree map, which isn't dependent on an outside hash function, and I think with just using the core library, like for at least for C programmers, we're going to be able to see like a lot of the things that you guys might be used to, which is like we're going to be creating we're going to be calling directly to the underlying kernel system calls and making abstractions around them and using that inside of a program. So let's first, I'm going to create I'm not going to put everything inside a lib, so I'm just going to create mod alloc, and then I'm going to create an alloc file. And I'm already going to import my first dependency, and I know like some C programmers might be allergic to that, but don't worry, I'm just going to be adding libc. It's pretty easy as well to like create a wrapper, or like we can create a header file and put all the includes of the headers that we want and then create a binding out of that using bindgen, but I'd rather just import libc. Everybody uses it. It just gives me the low level system bindings and nothing else. So this will be good enough. Oops. Okay. And with that, we're going to import a few things as well. So let me pull up my reference over here. For initially, we're just gonna actually I'll just write it. Yeah. And as you can see, like my editor's almost completing, so I'm just gonna get anonymous. Let me just make sure that. Oh yeah, I need read. So I'm gonna be importing mmap in the memory mapping function and memory mapping function for the Linux kernel. In the case of anybody who's like following along with me on Windows, you can use the Win API crate, and that's going to give you the bindings to all the functions in the Windows API. I'm not familiar with that, but I think you should be able to follow along with what I'm going at here. So I think first we should just start off with like, I think the way that I like structuring most of the programs that I work with is like I will allocate a big block of memory and then just and then create arenas from that block, and then like the arenas will be responsible for the areas of that block uh, that they currently own, and then when the program ends, that block will be freed, and like because it isn't running, I don't have to care about like any what the arenas were doing up until then, right? So I'm just going to just gonna create this alias. So it's like I'm gonna create a type over here called byte, and it's gonna be the same thing as U8, an unsigned integer, an 8-byte unsigned integer, which is just a byte. We can also, if I wanted to, we can make byte also be void, but I'll say that for the comments, but like I'm not sure if I'm not sure what the byte alignment of void is, if it's 8 bytes or it's 1 byte. And since I'm not sure, I'd just rather be explicit and use U8, which I know is going to be exactly 1 byte. And we're going to be making a struct called memory block. And inside of that, we're going to, and inside of that, it's gonna just be a buffer, which is a pointer to memory, a mutable pointer to memory, our capacity, so how big of a block it is, and the offset, which is the current position of the block that we have. And just gonna derive gonna use a pretty fun feature over here, which are derive macros. Because with Rust, you have to be explicit about all the things that you want to be able to provide to a struct. So if I want to be able to copy memory around, I have to explicitly declare that by saying that it's copy or it's clone and copy. And I also wanted to have a debug as well, so I can just print it and see what its current values are. But clone and copy are just giving or making explicit that we expect this to be copied around, and that copy is expected to be a byte-wise copy. So we're copying. This copy is going to be. I'm trying to think. I'm forgetting the term for it in C right now, but basically it's like there isn't any deep copies that we have to be making where it's like, oh, if we allocate heap allocated memory, then we have to do another heap allocation and then copy the elements into that new heap application, right? In this case, we're saying that like, no, that isn't gonna happen. This can just be a byte-based copy. Along with that, I'm gonna also define an arena struct. And that's going to just have like the same attributes down here. And let and okay, let's now implement a function for our memory block. So for our memory block, we're gonna create a function that's gonna initialize the memory block. That's gonna go down, call the mmap system call to allocate memory. So I'm just gonna do like memory block with capacity. And that's gonna take a capacity, that's gonna be U size, and then we're now gonna allocate that buffer. And to do that, we're gonna have to now call some unsafe code. And like I said before, unsafe is something that you should not be afraid of. It's something that obviously as C programmers, you are currently constantly dealing with. It's just that in Rust, and I think that is also the most important contribution that Rust made to programming languages, is like making it explicit the distinction between safe and unsafe code. I don't think people understand the importance of that, because C is unsafe by default, whereas Rust is safe by default. And unsafe should just be as like demarcating an area where it's like, oh, this could be possibly a place where we are violating memory safety, or yeah, just memory safety in general. Mm-hmm. And here we're going to call mmap. I think it's going to take the address, which can be null for now. That's be immutable. And then we have the length, which is going to be our capacity. Then we want it to be readable and writable. Remember that we want to. And then the flags, it's going to be anonymous. Oh, wait, and important shared, and this is incorrect, it's not private, because we do not want this memory to be accessible from other processes. So it's an anonymous private mapping. This isn't gonna be mapping a file into memory, and no offset as well. And now we can just and I forgot to put the return for this function as well. So it returns itself. So it returns a memory block. And itself, buffer, capacity, and then offset will be 0. If you get this right, what's the error over here? Mismatch type. Oh, okay. Let me. Okay, I can just cast this as U8. Does that work? Here. Another important thing to remember when you're using Rust is that everything is an expression, whereas in the case of C, everything is a statement. So people who are used to developing in C are more accustomed to seeing things as like a various sequence of operations that I'm working on, that I'm executing, and those operations will work on the data. Whereas Rust, everything is an expression and resolves to a value. And coincidentally, expressions are more expressive. But that doesn't mean they're better. Like, there's no like good or bad in this situation. It's just something to consider when you're using Rust, which is if you end a line with a semicolon, that means that it's going to return void. And in this case, in the block that, since I'm already in an unsafe block and this is the last statement, the last expression in an unsafe block, the return of this function is going to be the value of the block. So I don't need the semicolon. But yeah. And also whenever you're creating a struct, if the name of the variable is the name of the of one of the fields inside of that struct, you don't have to explicitly declare it. It will figure that out. So the same thing over here for capacity, I just have to set the offset to 0. And with that, we now have a memory buffer. And we can add a few more functions to this. And now, like, we can add we could add some functions like a buffer function to it where sorry, I'm getting more distracted by my baby's xylophone. She's playing it outside. But as I was saying, we can either create functions on this struct that will return us the value of what's in the buffer, what's in capacity, or what's offset, or we can just make all of these fields public. I'm just going to make them public for now for the sake of convenience. And now I'm going to be creating a new function that's going to be called arena, and that function is going to return an arena that's going to be allocated into this memory block. And we're just going to get the current position. The end of where we are going to be, where the offset's going to end at after this allocation is finished. So plus capacity. So in the first allocation, the current position is going to be, oh wait, it's going to be self dot length offset group. So yeah, we're going to get the current offset. In the first allocation, for example, it's going to be 0. And then the end of that allocation is going to be at 0 plus the capacity. And we're going to actually I'm going to make this return an option type. And an option type is just the for people who aren't aware, it's just a data type where you either return something or nothing. It's expressing the possibility of something not being there, right? So if, in the case of, if the capacity, or if the end is greater than the current capacity, we return it. We cannot, if we don't have any space left to be able to make an allocation, then we can't return an array. Then we're going to, wait, this is going to, it's a, like, we want a mutable reference to the current data, to the current struct that we're working with right now. So we're explicitly saying that here we're going to be modifying data, and that data is going to be now get a actually before, let me just put this as a placeholder. one of the things that I find very great about Rust is that like it's very easy to bring in various data structures from calling C code or C++ code into the Rust ecosystem. And one of the ways that like Rust facilitates that is that like it's for the implementation of some very important core traits. So I'm going to be important those. And one of those is going to be core. Let me get it right real quick. Which module is it in? It's in the house. And we want the deref. And so we want to be able to dereference mutably and immutably. And we're going to be implementing this on top of memory block. So implement deref for memory block. And in the case of deref, it has an associated type, which is in this case going to be the target. And the target is like, what is this going to ultimately dereference to? So we want this memory block to be able to be used as if it was just a slice of memory, because it is just a huge block of memory, right? So we know its start, its end, it's completely continuous. So we can make it be a block inside of Rust and be able to use it as if it were just another slice. So this is gonna be byte, and then now we implement the trait. And here we're going to be making another call to unsafe code, and that's going to be to slice from raw parts. And that's just going to take our buffer and our capacity. We could also, like, depending on however you would like to implement this, we can also make it so that instead of it being a slice over the whole entire block of memory, we can only make it a slice over what we've allocated up until now. So in that case, we would just replace this with offset. And now, every time that you do references, that you use this as a slice, it will only give you a slice up until where you've allocated. But in my scenario, I just wanted to be over the whole entire block. And we're going to be doing the same thing over here, implementing the mutable dereference. So in this case, it's just going to be going to a only change that we have to make is let me see if I just write everything correctly real quick. Use this up to and that's just going to return. Yeah. So now that we have memory block deref implemented for memory block, we can use it as if it were a slice. And in that case, if I want to get the buffer or the buffer inside of the buffer that I'm currently working with that will be used by another arena, I just need to so we're going to be creating a slice over that buffer, and that buffer is just going to be over where we're currently at up until the end. So, oops. So as you can see over here, like this is going to be returning me a slice over bytes, which are U8s. And now we would need, like, let's do this. Arena buffer. So now I have this arena buffer function, which is going to return me a slice of my of the in this memory block. It's going to return me the part of that memory block that's going to be allocated for the arena that I'm going to be using. But before I can do that, I need to implement some functions on top of arena as well. So let's do that. And that's just going to be like a public new function. Actually, probably better. I'm gonna to make it so that like it's consistent from with like the rest of the Rust ecosystem. I'm gonna also remove this like from raw parts and mute. And in this case, actually, I want this to be mutable. And we're going to actually, let's just do this from slice. Instead of making it an unsafe function and making it explicit, we can just do it so it's an arena from slice. So arena. That's going to return itself. And that's going to just now, one thing that I think a lot of people don't know about Rust is that like if you have a reference to something, all references are pointers. And just like in C, if you have an array decays into a pointer. So if you pass an array into a function that receives a pointer into C, it converts that array into a pointer. And we can say the same thing about references in Rust. If you have a reference and it decays into a pointer, into a raw pointer, because a reference is a pointer as well. So the only difference between a reference and a raw pointer is that a reference is statically checked by the compiler, whereas a raw pointer can't be. And since it can't be statically checked by the compiler, then it's unsafe to dereference the value because it could be a null pointer. It could be pointed to a space in memory that isn't in the process's memory, and so by it being since a compiler doesn't know if you're using it properly, that's up to you. That's what unsafe is. It's like, yeah, I got this. Hold my beer. Except like, unlike the times where you say hold my beer, usually I believe you're competent enough to not completely fuck things up. But yeah, this is gonna be a buffer. It's going to length to 0, and it's going to have capacity, which is the slices overall. Oh, is it pointer? Oops. Mutable pointer. What did I name it back there? Oh, it's also opposite. I keep on confusing the two. And we can also do the same thing over here where we just make it. And now we don't want this arena buffer function to be public. What we would like to be public is just an arena function. Arena, it's going to take immutable self, it's going to receive a capacity, and it's going to return a arena or an option of it. It's going to return either an arena or nothing. And we can just take advantage of the arena buffer function that we have as a capacity. And since it's going to be returning an option type, we can make use of map in this scenario. And map can be passed and we have our implementation. It's going to call arena buffer with the capacity that we receive in our function, and that return is going to be mapped to arena from slice. And for those who don't know, when you map over an option type, if it's none, you get none back. Whereas if it's something, then you run the function that you pass on that value. And Rust does the work to type check everything and make sure that like you can pass that value into that function. So you see now that everything is currently working properly. And do I have my test over here? Let me. Oh no, they're in a separate document, but I'm just gonna get some tests that are up. And I want them to be, in the case, like we can write unit test, and the way you would do that is that you would set this to test, create a module inside of this module, which would be called test. And inside of here, you would create functions that you would annotate with the test attribute. And when you write cargo, and then when you run cargo test, it would go through all of those functions and run them to, and if they fail, it will, if they pass, they pass, if they fail, they fail. But I don't want to write unit tests, I want to write integration tests. Because I want to be able to test, like, this is going to be a crate, and that's going to be ultimately used by other code, so I'm going to be creating a test folder. And that's okay. And oops. Let me make sure I got everything copied, and you know what? I don't even need a copy. I just need to properly copy the code over. And I can just do that over the shell. So I'm just going to open this, and here are the tests. Yeah. I'll be removing these two tests because we aren't going to be implementing them. That'll be for another day. These are good enough. And oh, I need to explicitly go over here. And now I need to make this module public. If it isn't, it can't be used outside of the crate. It can be used by other. Oh, and I didn't make. So I have to make sure that I'm properly declaring everything is accessible properly. So memory block and arena are both are going to be both public, and all the functions that I need to use over here are going to be public. And let me just change a few things over here. So it uses the public fields instead of applying functions. There's not going to be a link function. There's going to be an offset field. And now, okay, yeah, there's just going to be a few errors because there's some function that I haven't implemented yet, but we're going to get that right now. So let me just fix a few of these errors. This is obviously field. Now, as we're seeing over here, we're trying to use this arena as if it were a slice, and we have not implemented deref or deref view to be able to actually use it as if it were a slice. So let's correct that real quick. We should be able to just reuse this code that we have over here, but switch memory block for arena. And I fixed it. And now we just need to correct these things where these need to be declared as mute. And now we have to create just one more function on our arena, which is going to allow us to allocate. So that's going to be this allocate function. And just and this one, I'm just going to copy and paste. Copying between things is not as fun as it should. It's not as easy as it should be. Okay. Let me check something. So before we create alloc, we need to create a seek function. And this is just going to seek the offset value. It's going to set the offset value to the location in memory. We don't need to create a separate function for that, actually. I did my reference material here. Unnecessary. Where's it? let's just do the allocate. So allocate is going to be an immutable function. It's going to mutate the state of the data that we're working with, and it just going to, whoops. Let me put this on vibrate so I don't get interrupted. So count is going to be a generic function. So it's going to be generic over t, and it's going to return another optional value, and this is going to be non-null. Non-null is a pointer, is going to be, it's a data structure for a pointer that we don't expect to be null. And that's going to be 2t. Let me just get, I have imported properly, so pointer, no. For now, so remove the error, and then we get the size of what we, of how much we intend to allocate. That its alignment. Where we currently are in the pointer, so and now we're going to be calculating like how many bytes we want to actually allocate. And that's going to be the current plus the alignment minus 1. And then we do a bit shift so that we like get let me just write it first and then explain it. So what we're doing over here is that I write that properly. Yeah, I think that's it. So, oops. Oh, it isn't. Okay. So yeah, we get the size of the T that we're working on, good, and the alignment of it. So in the case of a 64-bit architecture that we're currently on, like the like 1 byte is aligned to 1 byte, 2 bytes is aligned to 2 bytes, 4 bytes is aligned to 4 bytes, 8 bytes is aligned to 8 bytes, and everything above that is aligned to 8 bytes as well. So what this basically does is that it guarantees that regardless of what we're allocating and how much we intend to allocate for it, it's going to always make sure that the new offset is going to be aligned accordingly, so that we aren't going to be allocating memory unaligned. And then we should now be able to see in our test if everything's been resolved, and then we can run and see if everything's working properly. I made just some simple tests to see if we're initializing properly and everything's set as expectedly. So if I create a memory block with a test capacity of 1024 bytes, the buffer is expected to not be null. Offset's going to be 0 since we haven't allocated anything yet, and the capacity will be the test capacity of 1024. Here we're testing if we're dereferencing properly, and if the length of that that slice that we're dereferencing to is the same as the capacity. And we're doing the same thing over here, and also mutating a spot in that block to see if we can do that. Then we test creating an arena inside this memory block, and if everything is initialized properly, whether it's referencing properly, immutably, and then we test the allocations. And I think the only thing I did not implement over here is a clear function, right? Because in this case, we allocate, see if things are allocated properly and clear, and then see if everything was clear properly. And then in these scenarios over here, we just exhaust them and see if everything is still working properly or working as expectedly. I think the only thing I haven't implemented yet is the clear function, right? So let's see, clear. Yeah, I haven't implemented clear yet. And clear is very easy in my gut. So clear. So I need to standard library I use. It doesn't. I guess swap doesn't. So let's just. The old is going to be self dot offset. Return the old, and the self offset is going to be 0. So in this case, we get what the current offset, and we return that. So we know how many bytes we cleared, and before we return that, we set offset to 0. So we go back to the beginning of the buffer and start writing over everything that we previously allocated. We could also, as well, maybe clear the buffer and just like set everything in the buffer to 0, but I'm not going to do that right now. So let's just build everything, and I re-imported. That's fine. Let's just keep that the way that this is. So yeah, we build. Oh, and just one more thing I'm going to be mentioning is that we need to also deallocate this. And to do that, we're just going to be implementing drop on the memory block. Drop is the function that's run whenever a variable is All scopes are declared with all blocks and scopes are created when you open up brackets, and if you declare a variable inside that bracket, it only lives until the end of that at that block at that last bracket, and once it goes there, it calls drop. So. And drop is immutable. What was it? Oh yeah, this is going to be unsafe as well. And then we just call it unmap. And it's going to receive the buffer and the capacity. Is that perfect? Also, it needs to return void. Oh, and I need to also cast it now back to a void pointer so that C knows what it's working. So now, whenever the block goes out of scope, it automatically deallocates that memory. What error is this? The trait copy. Okay, yeah, I don't need this to be copied. Need maybe this to be copied. No, this can be cloned as well. And now let's run this. Run cargo test. Our tests are failing. And why are they failing? It's just because I did not set I didn't declare the variable properly. I made it so it was, because all variables in Rust are immutable by default, I need to declare it as immutable. So let me just fix that real quick. So this needs to immutable arena. Are those the only errors? Now I think all of our tests are going to pass. So yeah, cargo run, cargo test. And all of our tests pass. And I think I'm gonna, yeah, I think I'm just gonna end things over here for today. And yeah, I'm interested if anybody has any questions, please leave them down in the comments and like, comment, and subscribe. And yeah, I want the opinions of both communities on what I'm discussing. Yeah, have a great day, everybody. I have to be a functioning adult and raise a child.